Good evening, everyone. Welcome to the Aquarium of the Pacific. I'm Jerry Schubel, President, and it's great to see all of you here this evening. We normally stream these lectures live also, and we're having some technology problems, but we're hoping to get that corrected. For those of you who are in the theater, we request that you silence your cell phones and refrain from texting for the next hour or so. I want to thank our sponsors, Gazette Newspapers and the Courtyard Marriott downtown. Without their support, we wouldn't be able to have this wonderful lecture series. I want to welcome Gregg Rao, who's going to discuss new management strategies for an ocean that has been impacted by climate change. Dr. Rao worked for 26 years at the Institute for Marine Sciences at the University of California, Santa Cruz. Most recently, he has held the position of senior research scientist there, and he also has a position at the Lawrence Livermore National Laboratory. He was a staff scientist for the International Atomic Energy Agency at the Museum of Oceanography in Monaco, and he was a National Research Council associate at NASA's Ames Research Center. He's the author of more than 400 publications in professional journals, including Science and Nature. He earned a bachelor's degree at Western Washington University in Bellingham, Washington, and a master's and PhD from the University of Washington in Seattle. In 2013, he was a winner in the geoengineering section and a co-winner in the electricity section of the MIT Climate Collab contest. He was a finalist for the Paul Allen Ocean Challenge in 2013, and everyone I know knows that Paul Allen just died a couple of days ago, and he was a finalist for the Keeling Curve Prize in 2018. Distinguished scholar, and he has a lot to say about how we're going to have to change the ways that we manage the ocean and the planet. Please join me in welcoming Dr. Gregg Rao.
Okay, good evening. Thank you, Jerry, for the nice introduction and the invitation to be here tonight. I'd also like to thank Linda Brown for coordinating our travel arrangements and logistics. And I'd like to welcome all of you. Thanks for being here. This is a bit of a homecoming for me. Many years ago, I lived in Santa Monica, just up the coast here, and worked at UCLA doing a postdoc there, so it's nice to be back here in Southern California. I'd like to talk tonight about climate change, CO2, and how that's affecting the ocean and what we might be able to do about it. So the title here is Sea Change Needed in Ocean Management. I'd like to thank Mark Eakin of NOAA for providing some of the slides I'll be presenting tonight. And let's see how this goes. Okay, well, for starters, we've all read the headlines here. The ocean is under a lot of stress, as we've read, and coming from a variety of quarters, overfishing, pollution, etc. And we can, for example, overfishing, we have a growing population. A number of countries obtain like 40% of their protein from the sea, and those populations are growing. There's an increasing demand for fish, shellfish, etc. And that's putting significant pressure on the natural populations that are out there. Pollution, all kinds of pollution, chemical pollution. We now find man-made chemicals throughout the ocean, throughout the food web. We're not sure what the consequences of that's going to be, but it's not a good thing. We need to be more careful about what we put in the ocean and more respectful of the marine environment in that regard. Noise, there's noise pollution that can have significant impacts on certain organisms. You've seen the stranding of whales and mammals on the beach as a consequence of using acoustics for looking for oil and gas, also military activities, but there are also other organisms that can be impacted by this noise pollution. Okay, land runoff. We've heard about dead zones that are off usually at the mouths of rivers. This is a consequence of land disturbance, agriculture upstream that brings in nutrients, increases productivity. That organic matter sinks and consumes the oxygen in the water column, and therefore it's very difficult for oxygen-breathing organisms to survive there. This is a concern. It's a concern around the world. And also plastic. You've heard the stories on plastic. We're putting in something like 10 million tons of plastic into the ocean. It degrades very slowly. Floating rafts of this are out in the ocean. It's breaking down, getting into the food webs. We have yet to know what the ultimate consequences are, but obviously those are probably not going to be good for the ocean. So we need to do a better job in addressing these pollution issues. And what I'm going to talk about tonight is perhaps the grandest pollution problem yet for the ocean, and that has to do with atmospheric CO2. You've seen the Keeling curve. Whoops, sorry. Let's see if I can use the, nope. Let's see if I can use the, whoops. No, there we go. Let's see if I can get the laser going here. There we go. Yeah, Keeling curve here. This is we have time here starting in the late 50s, going all the way out to, I think it's September of this year. Carbon dioxide concentration at a Mauna Loa in Hawaii, very pristine, capturing very pristine air. We see this progressive increase in atmospheric CO2. One of the most important earth science measurements of last century and probably this century also, and certainly marking the increase here that's dramatically increased over what it was. And we can take a closer look at how dramatic this is. This line right here is what I just showed you. And this is a record going back 800,000 years. So clearly the rate at which this is increasing and the absolute amount that it has increased sort of dwarfs anything that's gone before. And you'd have to go back millions and millions of years to get anything like this kind of level of atmospheric CO2. So from a historic standpoint, this is a really unique blip here. And of course, the primary cause of this increase in atmospheric CO2 is our use of fossil fuels, but it's not the only cause. Also land use. As we clear land, degrade the organic matter that's there, it returns CO2 to the atmosphere that otherwise would be stored in biomass. That is also contributing to the elevation in atmospheric CO2. But the primary cause here is fossil fuel use and industrial processes. Let's see if we can, there we go. So, this has gone on with a lot of knowledge about what the potential effects are going to be. We can go back to the 1820 here, where a French scientist realized that the Earth should be a lot colder than it normally is, and he concluded that there are gases in the atmosphere that cause the Earth to be warmer than it otherwise would be. It retains the heat that otherwise would reflect back out into space. A little later on, they discovered that this important gases were water and CO2. A little more research, 100 years later, it's really CO2 that is really the most concerning one of this because man has most influence on it. Others calculated that we may get a 4-degree increase in our CO2 per doubling of CO2. And further refinements and modeling of this has proceeded. Eventually, we've got here to some action. The Rio Agreement back in '92 realized that we need to keep greenhouse gases at below dangerous levels. And then we had the Kyoto Protocol, the recent Paris Agreement, et cetera. But as you can see, beside this as you can see, despite all this knowledge and attempts at action, the atmospheric CO2, the emissions here of CO2 has continued to increase, as has the atmospheric CO2 concentration. And this is just a little clipping here showing that I don't know whether you can read that or not, but this is 1912, and it's saying coal consumption affecting climate. This is like over a century of knowledge here, and we have yet to really effectively come to grips with this problem. And it is warming our planet. This is a record of mean atmospheric or surface temperature. We've gone up approximately at 1 degree C since pre-industrial time. There are obviously some blips here. CO2 isn't the only cause of a mean temperature here, but it is a primary one, and now the signal of our atmospheric CO2 is really coming to the fore, and will continue to do so as we emit CO2. And this is simply a graph of our best estimate of how sensitive mean surface temperature is going to be as a function of cumulative anthropogenic CO2 emissions. So this is just summing up all that's gone, starting back in the pre-industrial age, back in the 1750s. We're up into this area right now, and if we continue on, we will continue to get this warming. Obviously, there's uncertainty here. But the bottom line is certainly if we continue business as usual here, which is this red line up until the end of this century, we will be above 4 degrees C of warming, which is very concerning. Another feature that's very important for the ocean is that most of the heat that's been trapped by greenhouse gases has gone into the ocean. More than 90% of it has gone into the ocean. And this is a graph. This represents the surface ocean. This is the deeper ocean. And these layers down here are like the atmosphere and land, et cetera. So you can see the vast majority of the warming that we're doing to the planet is going into the ocean. And that's also very concerning given the temperature sensitivities of some of the processes there. And as an example, this is a satellite image that identifies critical temperature thresholds. Let's go back here. There we go. Yeah. These are colors denoting increasing thermal stress, and this relates to corals. And at level 2, we were getting widespread coral bleaching and mortality expected. And as you can see in this time frame, like 14 to 17 or so, good chunk of the ocean here is way over critical thresholds here for marine corals. And, certainly mortality did happen. There was several mortality events here in the Great Barrier Reef. We're concerned about corals because even though they occupy a very small part of the ocean, about 25% of the marine diversity resides there. All sorts of fish and invertebrates and plants, etc. So if we lose corals, we're going to be losing a good deal of the biodiversity of the ocean, and that's very concerning. And okay, here's another example. This is sort of a before and after picture here of a thermal bleaching event. Now this is in Jarvis Island. This is out in the middle of nowhere, middle of the Pacific. It's uninhabited. It's managed by the U.S. Department of Interior. Pristine coral reef. But despite being otherwise untouched by man, it was largely devastated due to the thermal event that it experienced back in 2015. So obviously this is very concerning for ocean ecology. Another thing that warming does is reduce sea ice cover. And this is a graph of the extent of summer sea ice in the Arctic. And as you can see, going from 1979, I can't read the end here, but it's fairly recent. You can see there's a general trend here declining. The sea ice is declining in the summer, and this is concerning because it's opening up this ocean really for further warming. If you have it covered with ice, it's a reflective surface. If it's open, you have a dark ocean exposed, and that's going to absorb more heat and will warm more quickly. And this has biological impacts. For example, marine mammals. Many marine mammals rely on sea ice cover for their existence and for their migration and living. And here's some examples of where marine mammals are being forced into other behaviors that where ice is absent. The other thing that we need to be concerned about as the ocean warms is that it expands and therefore sea level rises. Here's a record of sea level rise going from the 1990s forward here. The sea level's rising for two reasons. One, as I said, thermal expansion. As waters warm, they expand, but also we're melting glaciers. Water that's otherwise stored on land as ice is melting and running into the ocean, and that will also obviously increase sea level. So very concerning here, and we don't have to look far to see what the impacts of those are. Obviously, we've just experienced a storm in Florida where they had significant flooding and storm surge. Here's some other examples. A lot of our infrastructure is located on the coast. And there's trillions of dollars of infrastructure, and those are all under threat as sea level rises. And that's not to say also that there are biological consequences of this. There are animals that rely on sea level being at a certain level. If we start raising that, they're going to have to migrate up or otherwise adapt to the situation. So there's a lot of marine biology concern surrounding this. And as if that weren't enough, another concern about CO2 in the atmosphere is that you're adding also CO2 to the ocean. That is, as you add CO2 to the atmosphere, that the pressure of that CO2 is such that it drives some of the CO2 into the ocean. But when that happens, it doesn't stay as molecular CO2. It combines with water to form an acid. It forms carbonic acid. So as a consequence of our putting CO2 into the atmosphere, we are also putting CO2 into the ocean, and we therefore acidifying the ocean as a consequence of that. And this is just a graph showing that as we increase the dissolved CO2 in the oceans, we're going to drive down the pH. Now, pH is the opposite of, as pH goes down, acidity goes up. But it's a pretty well-established relationship here, that as CO2 goes up in the air, it's going to go up in the ocean, and we're going to increase the acidity, at least in the surface ocean. And that's exactly what's been observed here. Here's the Keeling curve that I just showed you. And these are direct measurements of CO2 in surface waters off of Hawaii at the Hawaii Ocean Time Series, the HOTS station. And it's the CO2 in the water, and this is the acidity in the water that's being directly measured. And as you can see, we've lost, we're approaching almost a tenth of a unit of pH. Now, to put that in perspective, if your blood were to change by a tenth of a pH unit, you'd be dead. A lot of biology is very sensitive to pH, and it doesn't take much to really alter things. So this is, again, very concerning about the biological impacts that are going to occur because of this. And a number of studies have shown that you're actually going to get corrosion, loss of shell material for those organisms that form shell, and it will also make it very difficult for them to make shell. So this is having an impact on shell-forming organisms. Now, I've got a caveat by saying that not all organisms are sensitive to this. Just some of them are. They've done a lot of experiments. Some seem to thrive just fine, and others are sensitive to it. But the bottom line is that we are going to change the species composition of the ocean if acidity continues to increase. And this is just a sort of a longer-term look at what I've more or less just talked about. You've got global average surface temperature change, and these are under two scenarios. One where we rapidly reduce our emissions to zero by the end of the century. We keep warming below 2 degrees C, and the red is more or less business as usual. And in this case, we're looking at average surface temperatures here. We're going up, whereas here, maybe we have a chance to stabilize or go down. We're looking at, I think this is pH. I can't read that too well. Hemisphere, sea level, sorry, sea level, yeah. Sea level in high emissions versus reduced emissions scenario. Means sea level rise here, going up. And this is pH. Again, if we are able to reduce our emissions, it will stabilize at somewhat lower values, but otherwise it's going to go down. A couple of these are worth noting that even though if we were to go to the low emissions scenario, mean sea level rise is going to continue to rise because there's a lot of thermal inertia here, that ice doesn't instantly melt. It takes a long time to initiate melting of ice, but once it gets going, it's hard to stop. So even though we were to have our emissions go to zero here, we would still have probably another century or two of sea level rise to deal with. The other thing I should point out is oxygen. As oceans warm, the solubility of oxygen goes down. So therefore, the oxygen concentration in the ocean goes down. That's obviously concerning for any biology that breathes air or breathes oxygen. Another concern here is the longevity of CO2 in the atmosphere once it's placed there. Now, these are two different trajectories. One, a relatively small instantaneous injection. I think it's 100 picograms of 100 gigatons of CO2 versus like 5,000 gigatons. This would represent more or less what would happen if we were to burn all the fossil fuels. There'd be this upper scenario. But in either case, I guess I also need to say that we've emitted right now about 500 or 600 gigatons. So the current trajectory would be right along in here. Bottom line is that once you emit CO2, a lot of it stays in the atmosphere for hundreds, thousands of years. So this is not something that's going to go away once we stop emissions. It's going to linger in the air. It's going to continue to warm and acidify the planet. So that's a concern. Okay, so based on all this, what should we be doing here? Well, it's pretty obvious that we need to reduce our emissions of atmospheric CO2. And we need to also see if we can increase the removal of CO2 from the atmosphere. As I said, it's a very long-lived gas, and if we really want to rapidly reduce the impacts of temperature and acidity, we need to think about ways that we might be able to really proactively remove the legacy CO2 that's already there. And we also need to explore new ocean management practices that could help address this, as well as to help prevent or reduce the impacts of climate change that is occurring and will continue to occur in the ocean. So this is really, as I say, an all-hands-on-deck moment here for the oceanographic community. This should be front and center of any sort of thought about ocean conservation and ocean management. So with that in mind, I was curious what various conservation organizations, what their philosophy was here. Clearly, they recognize that climate change is here and is impacting the ocean, but what are they recommending here? Well, climate change in the ocean can be addressed with the same effective tools as many other threats in marine life. Well, I beg to differ there. We have a lot of tools for managing the ocean to address overfishing, pollution, erosion, things of this nature. But the warming and acidification of the ocean is something totally different. And I would argue that our current management practices are not ready to, are not up to addressing those impacts and should be concerning here. The establishment of global networks of no-take marine reserves is an important step. Ecosystems that are healthy and robust, et cetera, et cetera. You can read that. But anyway, the idea is that if we have a pristine ecosystem, everything's going to be fine. Well, we just saw coral reefs, pristine coral reefs that are now dead, with that philosophy. So clearly, playing the same management game that we've been playing all along is inadequate for addressing the problems that we're up against now. By improving the quality and quantity of marine protected areas, we will conserve marine biodiversity in a rapidly changing climate. Well, I don't get that. If the ocean is warming and acidifying above certain critical thresholds, we need some new management tools to address that. And then there's a discussion here about how we need to better understand the ocean and have more predictive capability. Well, I would argue that we have some pretty good prediction right now if we continue on this CO2 track. It's pretty clear that the ocean is in trouble now and will be in worse shape as we continue. So I'd say let's try to divert some of this attention and to try to thinking about what action we could possibly take here to avert some of these problems. And this is just pointing out that here we have a listing of heritage sites, of coral reefs in heritage sites, which are the best managed in the world. And you can see that a majority of them over here on the right, and I can't read the dates, but I think it was recently, each of those experienced very critical warming, and many of them were damaged because of it. So here we have pristine environments that are already managed as marine protected areas that are being devastated as a consequence of the thermal increase. So we need to think about what we can do to help avert this. And so again, I just say, here's what we need to do. And so how could we do it? And how could the marine environment help us address some of these issues? Well, first off, if we want to address this CO2 emissions problem, clearly we need other sources of energy other than fossil fuels that don't emit CO2 or are very low emitting CO2 sources. And the ocean is very rich in renewable energy. It's got many times more energy potential than what the whole globe consumes in a year. And there's a whole variety of it. We've got wind, wave, solar, thermal, et cetera, just out there. And there are technologies that can tap into that. So here is a way that the ocean could provide us with a way of reducing emissions by harnessing the huge amounts of energy that are out there in the ocean. Another concern, well, I guess I've already mentioned it, but as we continue emitting up here and going out in time, and our emissions continue to increase, as we do that, it becomes less and less likely that we're going to stay below a certain thermal threshold. This happens to be 2 degrees centigrade. It's very difficult, if not impossible, as we put off turning this curve down to reach this level of warming and hold it there by just emissions reduction alone. And for example, this red line shows that we actually need to have negative emissions here to reach this 2-degree target. And by negative emissions, I mean we have to proactively remove CO2 from the atmosphere. It's a lot easier to avoid emissions, but we've reached a point now where it is unlikely that that's going to keep us below this critical threshold. And so now we have to think about ways, if there are any ways, that we can use to proactively remove the legacy CO2 that's otherwise just going to stay there for a long time. Now, there's some good news in this, in that nature naturally does remove some of our CO2. Actually, about 50% of the emissions that we put into the atmosphere is taken up by the ocean and land processes. And you can see that if you blow up the Keeling curve, and this is just looking at, I think, 2 years worth of data. On an annual cycle, yes, the CO2 goes up, but it also goes down by more than 5 parts per million here. This is CO2 drawdown. This is a carbon dioxide removal that naturally occurs. And if that hadn't occurred, obviously we'd be in a much worse shape. So this is encouraging that carbon dioxide removal is already part of what Mother Nature does. And so that gives us thoughts here. Maybe we can enhance that or add to that to help us remove legacy CO2 more rapidly. And this is just a historical perspective on how much has been taken up by the ocean and the land. As you can see, a majority of it's gone into the ocean. Now that's a good thing because it hasn't stayed in the atmosphere and warmed the planet, but the bad thing is that most of this is in the form of carbonic acid. It has acidified the ocean as it's done that, so that's not a good thing. Less CO2 has gone into has gone into the terrestrial environment, but it does contribute, and there's certainly a number of ways that we can increase that uptake by carefully managing the land, and there are other technologies that could assist in increasing this uptake. Again, this just shows the relative proportion of land versus ocean uptake for a given input of CO2 over the span of, I think it's 1,000, or how many thousand years here. But again, the atmospheric CO2 slowly goes down because of these uptake processes, and again, the ocean is already taking up a majority or will take up the majority of the CO2. So are there ways that we can enhance this, but also do it in a way that doesn't acidify the ocean? That's the question. So one possibility is, why not just extract CO2 from the ocean? If it's in there, there are physical and chemical ways we can pull it out of the ocean. It's very energy intensive to do that. It's probably not going to be a solution on a very large scale, but there could be local areas where we could manage the chemistry in very localized areas by extracting the CO2 and storing that in some way. So there's just some ideas here that people have talked about. Another angle is to harness biology in consuming CO2. Marine plants, microorganisms, anything that photosynthesizes consume CO2. So that's a good thing. Unfortunately, most biology is designed to rapidly recycle that carbon back to CO2. But we could intervene in ways that could maybe store the carbon longer, or we could harvest it and put it in more storable forms on land, etc. So there have been lots of talk about and thoughts and actually experiments where marine plants are grown intensively and for the purpose of storing carbon or providing other source, for example, fuel or other uses here. Now we use this as fuel that simply returns CO2 to the atmosphere, so that's not really a carbon dioxide removal strategy. But if we either keep it as biomass or convert that to some longer-lived form of carbon, we could actually affect carbon dioxide removal. Another way to consume CO2 is abiotically, and this involves geochemistry. Now, we're lucky that most of the Earth is composed of what is called alkaline rocks. They are really a chemical base, and they react with CO2 to form other stable compounds, and therefore, over long periods of time, actually consume CO2 out of the atmosphere and form what are called carbonates and bicarbonates. So that's good. It's actually one of the major ways that Mother Nature naturally consumes CO2 over long time scales. But the problem is that it does take a long time for this to happen. So I and others, many others actually, have been thinking about ways that we could accelerate this otherwise natural process to increase CO2 removal from the atmosphere. And this is just some more details. Basically, the idea here is that if you have an acid like carbonic acid and you react that with a chemical base, you're going to get a neutral salt. And in this case, it's a bicarbonate. that you're forming. But there are various sources of bases. One is natural that we just talked about. There are various minerals that are naturally alkaline, but you can also synthesize bases and do the same thing. These are going to be more expensive and more energy intensive to make. But there are various schemes that are thinking about how we could use this chemistry to accelerate the removal of atmospheric CO2 and therefore better, more quickly lower the atmospheric CO2 concentration. Interestingly enough, these reactions that I just talked about are already used by marine aquariumists, saltwater aquariumists. They're interested in adding calcium bicarbonate or carbonate to their aquarium to help balance the chemistry, help neutralize the acidity, and add calcium for their calcifying organisms. But the angle here is, again, to add these chemicals, not necessarily to consume CO2. In fact, they buy tank CO2 to do this reaction. Well, we could potentially scale this up to a much larger scale and maybe have larger, maybe even global impacts here. Here would be our reactor, and rather than using tank CO2, we could use CO2 from a power plant. And by doing this reaction, we could consume the CO2, we would react it with our calcium carbonate here, limestone, and we would put the alkaline material into the ocean just like we would into an aquarium to help rebalance the chemistry there and help neutralize the acidity and the impacts of the acidity. Another idea, and this gets a little complicated, but I and others have shown that you can take some pretty common materials here, base minerals, salt water, and we have lots of renewable electricity out in the ocean. And doing an electrochemical process, we can make hydroxide that's very reactive and absorptive of CO2, so we can generate this calcium and magnesium bicarbonate, but also generate hydrogen, which can be used as a fuel in substitution for fossil energy. So if we drive this with non-fossil energy, we have a carbon-negative energy generation system that also generates a chemical that could potentially be beneficial to the ocean and that counters ocean acidification. And this just points out that hydrogen has multiple uses here. We can use it directly as a fuel. California is now getting hydrogen cars from Japan. They're trying to get a foothold here in the state. The state is building out a hydrogen fueling infrastructure. So there's a potential here that hydrogen use will grow in the future and can become a part, at least, of our transportation fuel. The other role here is energy storage. This is very important for renewable energy because many of our renewable energy forms are periodic, like solar, wind, etc., and you need to store energy while the sun shines so that you can have energy available when the sun isn't shining. And this is one way to do that. We can use that off-peak energy to generate hydrogen and then reconvert that to electricity using fuel cells at times when energy demand is high. So there's various ways this could fit into, to do multiple things really in terms of substituting for fossil fuels, consuming CO2, and helping mitigate ocean acidification. Another set of possible actions here is to cool coral reefs or cool ecosystems that otherwise would otherwise be over their temperature threshold. And here's an experiment where bleached corals cold water is brought in, and after a time they actually recover because they are able to cool and to regain some of their activity that they had lost during thermal bleaching. So we could, again, expand this to a larger scale. Could we have solar-powered pumps where we're bringing up cold water from the deep, spreading that over the coral reefs and helping moderate the temperature there and thus save them from bleaching during critical times when otherwise the temperature would be over critical thresholds. This actually is being seriously considered for the Great Barrier Reef. They're going to do some experiments in this regard. Another way to cool the surface ocean would again be bringing up cold water to the surface, but we can actually harness that to also generate electricity. When you have a thermal gradient, there is technology available that allows us to drive a turbine that drives a generator, and we can generate electricity. And therefore, again, this does multiple things. We're cooling the surface ocean, but we're also getting energy out of doing that. And we've proposed, well, heck, if you've got electricity, you can do our negative emissions hydrogen thing. So here we can do a whole bunch of things. We can make non-fossil fuel, consume CO2, reduce acidity, and cool the surface ocean all in one fell swoop. Well, okay, it's a little far out, but there you go. Another angle for addressing thermal impacts is to simply shade the reefs. Put some netting or something that cuts down on the direct solar input to that reef. And so various experiments have been done doing this. Obviously, not all the warming in a given area is due to the solar energy that arrives right there at that site, but normally it will warm the ocean elsewhere, and the currents will bring that warming in. So it's unclear how effective this might be at the small scale like this. But others, others have talked about doing this at much larger scale using cloud generation or aerosols that would provide shade, that would reflect excess solar energy back out into the atmosphere, and therefore prevent warming or reduce the warming that would be occurring above or below these clouds or aerosols that are put into air. So this is another way that's being considered for cooling certain areas of the ocean. And last but not least, how about genetic modification of organisms? How about seeing if we can make them more resistant and more resilient to temperature and acidity, et cetera? There are a number of groups now that are looking into ways that we might be able to do this to help them, to a sort of assisted evolution here, to help them overcome these thresholds, and maybe some will be able to survive in certain areas, or we'll see. But anyway, it's being considered here as a way of addressing this problem. So recommendations, more or less I've said this before, but we need to acknowledge that human-caused climate change is significantly impacting the marine ecosystems and threatening ocean conservation. We need to advocate for the reduction of our emissions of CO2 to the air. That needs to be part of any ocean management strategy. And we need to seek and support new and unconventional ways that we might use to help mitigate these effects or otherwise help organisms survive given the threats that they're now facing. And I guess I wouldn't be complete unless we talked about what we can do individually to lower our carbon footprint and therefore help the ocean. And a study in last year identified a number of things we can do. You can live carb-free, buy a more efficient car. I'm sorry, I can't read all this, but the size of these circles identifies the relative importance or the amount of carbon that you can avoid emitting just by your own personal activities. So what's the big circle here? And that is having one less child. That's a biggie here. And I think it tells us that we need to reproduce responsibly if we're going to save the ocean and save the planet. I'm going to skip this. This is just some discussion about how, well, maybe I'll talk about it. Whoops. No. Going from here to here are increasing impact of various activities, some of which were in the last slide. And these researchers wanted to see how frequently these were mentioned in literature. And as you can see, it's kind of scattered here. The ones that are actually the most impactful don't always get the mention here in the educational and government literature. So we could do a better job in communicating to individuals, how impactful their various activities are, and that this obviously needs to be improved. So I'll just wrap up here. Bottom line, we need to acknowledge that CO2 and other greenhouse gases is affecting the ocean and the planet, and we need to strongly advocate for the reduction of our CO2 emissions if we care about the ocean and the planet. And we need to realize that conventional marine management isn't very well designed to address these new unconventional threats. And therefore, we need to think about and see if we have any additional options that might be useful in helping us address these problems. And obviously, lastly, each of us has a role to play here in reducing emissions and helping save the ocean. So thank you very much for your attention.
So, Gregg, it's very clear that we have to quickly eliminate further greenhouse gas emissions. We also have to actively begin to remove CO2 already in the atmosphere, stored away, and remove CO2 from the ocean if we don't want to completely change marine ecosystems. There are a variety of tools. There's probably no single strategy. But what's the major impediment? Is it financial, technological, or lack of political will?
Yeah, possibly all of that. I would say the most important thing is policy. I think, this country, the world, I think most of the world has recognized this as a problem. Not all countries have, but this needs to be recognized as a serious personal, national, international problem, and there need to be policies that support the development, the application of technologies that we already have, for example, renewable energy, but also realize that that's probably going to be inadequate and that we need to start looking for new management technologies that can help us address this. And I think if we fail to do that, we're in very serious trouble. We may be in serious trouble anyway. There may be not enough new ideas and new technologies to solve this problem, but we're never going to know that unless we really try. And that starts with policies that really support and advocate for that kind of search and that kind of research and development.
Policies that are binding, because as we know, with some of these other, like the Paris Agreement, there are no teeth in it. So it's easy to make these promises. All right, who has a... Wait, we got one here and then back there.
Thank you very much. It was a great multifaceted overview of the problems and some of the solutions. But except for one brief reference at the end of it, it didn't talk about the 800-pound gorilla in the room, population. If the Industrial Revolution is the benchmark of the start of this rapid change, when the population was only 1 billion, 150 years later it's 7.5 billion, half of that in yours and my lifetime. That Keeling curve looks pretty puny next to the population hockey stick. I think there ought to be a little more emphasis earlier on in the talk about the population, because if we cut pollution in half and we double the population, we haven't solved the problem.
I agree. Certainly, reproduction needs to be part of the discussion here, an important part of the discussion. And as I showed in that one graph, how frequently it appeared in textbooks and literature, it was 0. That's not very realistic. It definitely needs to be discussed and needs to be recognized and acted upon.
Your lecture was absolutely quite informative, and I want to thank you. And I had 3 things I wanted to mention. You mentioned about marine life migrating if something's not done. So is there specific marine life that we need to be concerned about? And the other thing I'm wondering about has to do with hurricanes and the effect the hurricanes are having on the ocean. And also China no longer is taking plastic. So what's the backup plan the U.S. has? Because more than likely the level of pollution is going to increase. Thank you.
Well, you've hit a lot of important issues there. Plastics. We keep putting it in the ocean. We need to be very careful. We need to be much more careful about doing that. And it's a real problem because the plastic obviously is very long-lived. It ultimately breaks down into small particles and gets into the food web. And we don't yet know what the full consequences of that are going to be. Certainly what we've seen so far is very negative. The other part of your question was about migrations.
Well, on the plastic, what's the backup plan? Are you aware that the U.S. has, since China is no longer taking our plastic? We're looking at hundreds and thousands of tons of plastic now we have here. So do you know, have you heard of anything?
Well,
any
certainly we can
plans that's being
recycle
made?
at least some of it. A lot of it could be recycled. Now it can be energy intensive, so we have to think about how we recycle it. If you can use renewable energy to do that, that's great. If you're using fossil energy, then it's not so great. Maybe there could be a greater push for biodegradable plastics. It doesn't have to be long-lived plastics. I don't know that technology, but I know that there are biodegradable plastics and companies that are working on that. That would seem to be one way to go here, is to transition to less long-lived, shorter-lived plastics that would break down and wouldn't stay out in the ocean for hundreds of years.
So that in regards to hurricanes, what effect is this massive hurricane we have having on ocean life?
Yeah, well,
And
it's no doubt.
anything we can do to
Yeah.
keep it from being so
Yeah.
catastrophic?
Yeah, well, it's a little outside my area. I'm sure my fellow marine biologists are looking at the aftermath of these hurricanes. I don't know what exactly they're finding, but you can imagine it's quite devastating, going to be quite devastating to marine life there. Now, it will recover more or less, but to be honest, I don't know. I'm not familiar with the details of those studies, but certainly it is very concerning, and we're tying it back into CO2 and warming. As the oceans warm, the intensity of these hurricanes are going to get much stronger. So we can expect much stronger hurricanes and therefore more impact to marine life as well as humans.
And I think particularly marine life in nearshore areas. So coral reefs, mangroves, wetlands, those are the ones that the hurricanes take the greatest toll on, because not so much on midwater and deep water. Who has the next question or comment? You're very quiet, Holly.
Well, it's not directly on Dr. Rao's talk. It's more of, since there's so many young people in the room, I wanted to...
Tell them who you are.
I'm a researcher at UCLA, the Institute of the Environment and Sustainability. And one of the topics I've occasionally taught is population and development. So I just wanted to point out that a lot of the billions of people in the world scarcely have any carbon footprint, right? Because they don't have access to fossil fuel energy. And so it's really an issue about overconsumption by a small percentage of the global population that needs to be addressed. And we know that also when people have a good standard of living and women have access to reproductive care and freedom to make choices about their family size, you really do get decreases in how many children they have. So that's why, Europe and Japan, their fertility is below the replacement rate. They're going to have a hard time maintaining some of their social systems because they don't have enough children in the way of looking at it. So the number one thing you can do with population is really give women access to care. Education, yeah. So, thanks.
And that has been proven very conclusively in Latin America. But there's a study recently that showed that 50% of the girls in the world under the age of 10 today live in countries with severe gender inequity. So they don't have the opportunity to go to school, and women, as young girls and women, don't have the opportunity for careers. The replacement rate, 2.1 children per couple, and the 0.1 is because there is some infant mortality. But if you look at places in Africa, even though the reproductive rate has gone down, it's still above 5 children per couple. So we've got a lot of work to do, and if you look ahead, what climate change is going to do to agricultural productivity, the places with the highest birth rate are the places that will lose the most food productivity because of climate change, primarily throughout much of Africa. So we've got lots of problems for you young people to deal with. You're welcome. You can thank some of us for giving you a wonderful set of opportunities. Who has the next question or comment? Okay, I got one back here.
Yeah, I just want to comment. I think that probably by your slides there, one of the most effective ways of physically removing CO2 at a very economic level is not burning up the rainforest. Plants naturally absorb CO2. We all know that they put oxygen back into the atmosphere. It's non-technical, doesn't cost anything, and you don't put smoke and all that stuff into the atmosphere and CO2 from burning wood to clear the forest. So if there's some way that we can encourage indigenous peoples in South America, Africa, et cetera, land clearing on a wholesale level to mitigate that destruction of the rainforest, I think that that would help quite a bit.
Well, certainly better land management is going to lead to a healthier ocean. So there's a lot of things that we do on land that impact CO2 emissions that ultimately impact the ocean. My focus here was mostly on potential marine-based solutions, but I certainly agree there's a lot that could be done on land to preserve carbon sinks that are there and also to potentially enhance them so that they're drawing out even more CO2 than they currently are. Right. 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 The argument there. Right. The argument there is that we're already committed. We already need X amount of land to grow our food and fiber and provide housing. And the concern there is that how much are we willing to give up of that to have dedicated carbon sinks on land? Certainly there's some capacity there, but you get into conflicts there with other uses, and that's always a concern with that.
But it can contribute to solving the problem.
Yeah.
You can't solve it, but it can contribute.
Yeah, it can be a
And
big
if you
part.
look at, on an aerial basis, what ecosystems have the greatest ability to remove and store CO2, they are mangrove forests and wetlands. And we've destroyed most of our mangroves throughout the world, and here in Southern California, we've destroyed 95% of our wetlands. So as we go forward, there's great opportunities, especially with sea level rise, to try to create new mangrove forests and new wetlands. Other question or comment? We got one there and then one over here.
Dr. Rao, are there data available yet from the Orbiting Carbon Observatory that shows the major sources and sinks of CO2 around the world?
What was the first part of that question?
Are there data available from the orbiting carbon observatory
Oh,
that
the
show the
satellite.
major sources and sinks?
yeah, I would say no doubt. I don't know that data and technology, but I understand that there are satellites that are able to sense CO2 concentrations in the atmosphere spatially around the Earth, and to do that, over multiple years, would be it could be used to understand sources and sinks of carbon in a much finer detail than what we now know. But I must say I don't know the details of that.
We're going to take one more.
All right, so in your presentation, you talked about like substitutions for fossil fuels, which include like using like ocean waves or like solar panels and things like this. But won't some of these inventions like harm some of like the ecosystems or like the animals like in these sort of environments?
Yeah, obviously, to do any of this stuff, you have to understand what the environmental consequences are, and you have to weigh those against what the benefits are. There's definitely a cost benefit to any of these actions that I've talked about, and a lot of them at least some of the ones I work on, those are not very well known. Some of the renewable energy area, those are better known because they've been practiced for a longer time. But certainly, in anything we do here, there's always a potential or an actual potential or real impacts that can occur. And again, decision makers, you and I and everybody else, are going to have to decide: do we want less CO2, and weigh that against some localized impacts to the environment? And it's very likely that we're not going to be able to avoid all these impacts, and we're going to have to make some decisions and trade-offs as to how to actually proceed here. So you're right, these trade-offs have to be understood, and we need to evaluate those in making our decisions.
We have one more, okay.
So why do some smaller nations have larger
Hold the microphone close to your mouth.
Oh, sorry. So why do some smaller nations have larger per capita emission estimates more than like industrialized nations like the U.S.?
Why do we have more emissions than other countries that
Yeah.
have more people? Well, we have a higher standard of living. We're more dependent on fossil energy per capita than many. So yeah, there's quite a variation, obviously, in the carbon footprint of different countries and the peoples with, per capita within those countries. So that does vary significantly.
So we in the U.S. have the highest per cap of emissions, so per person. China as a country has the greatest amount of emissions because they have a much larger population, but their per caps are lower than in the United States.
Thank you.
And of course, the challenge is everybody wants to have our high standard of living, but if that were to happen using fossil energy, it would be untenable. So we've got to figure out a way of allowing people to improve and have a higher standard of living, but doing so with a much lower carbon footprint. That's the challenge here.
Well, I want to thank you all for coming, and Gregg, thank you for a very illuminating lecture. Gave us lots to think about.
This is going to be over their heads.
No,